In this video, we're going to talk about how to interpret Cronbach's alpha. And first, I'm going to kind of give you rules of thumb for Cronbach's alpha. So you calculated it. Now, what does that number mean? So remember, Cronbach's alpha is a prediction about a retest reliability correlation. So correlations are between -1 and 1, but you would hope that your tests are positively correlated, right? If you take the ACT once and then take it again the second time, hopefully they're going to be positively correlated and not negatively correlated, right? If you are doing good on the test, the next time you should do good on the test as well. Like, it's not going to mean the people who did really well are going to do really bad now, and the people who did really bad are going to do really well. That would mean it's negatively correlated. So that's not going to happen. So anyways, the number for the Cronbach's alpha will always be between 0 and 1. Because it's always going to be a positive correlation, and correlations that are positive are between 0 and 1. So if we have anything above 0.9, that's considered excellent. If it's between 0.8 and 0.9, that's considered good. And if it's between 0.7 and 0.8, this is acceptable. 0.6 and 0.7 is kind of questionable. Between 0.5 and 0.6 is poor, and anything below 0.5 is unacceptable. So remember, this is a measure of reliability of your scale. And it's trying to predict the retest reliability based on the internal consistency of your test. So it's looking at the inter-item correlations. So we'll talk about that a little bit more a little bit later. And remember, we had Cohen's rules of thumb, since these are much different than Cohen's. So we have much higher standards than Cohen's rules of thumb for correlations between two different psychological constructs. This is because Cronbach's alpha is a prediction of the correlation between two tests about the same psychological construct. So you hope that if you're measuring the same exact thing, the correlation for between the same exact constructs are going to be higher than the correlation between two different constructs. So that's why Cronbach's alpha has higher standards than the rules that we learned about from Cohen. Now I'm gonna kind of give you some cautions about Cronbach's alpha. You don't have to memorize all these, but just know it's not perfect. So it's really predicting the retest reliability from all the split half reliabilities or from all the inter-item correlations. It's not an actual measure of retest reliability. It's just a prediction of it. So it's not really about, okay, if we take this test one time, will it correlate with the test the second time? It really only tells you about the internal consistency or the internal reliability of your test or your scale. So it's trying to predict what your retest reliability is, but in reality, all we are measuring is the internal consistency, the correlations between your items on your test at one time period, not multiple time periods. And as your number of items increases, so will Cronbach's alpha. So adding more items will always increase Cronbach's alpha. It also does not consider the number of people the correlations are based on. So a large sample would be needed to get a good estimate of the average inter-item correlation. So you wouldn't want to base Cronbach's alpha on like 3 people, right? That doesn't make any sense. A common suggestion is 300 people, but this isn't a hard and fast rule. And a lot of times you're not going to get 300 people, and a lot of times we base Cronbach's alpha on a lot less people. Alright, so here are some more cautions. So Cronbach's alpha tells you nothing about what's called the dimensionality of the scale, and that could mean that you could actually have two separate constructs, on the same scale, and you wouldn't know it by just calculating Cronbach's alpha. So say we have items about job satisfaction and life satisfaction on the same scale. You calculate Cronbach's alpha and it's actually high. And that's because job satisfaction and life satisfaction are going to be correlated with each other. So their items will be correlated with each other. But that doesn't mean that these items should be on the same scale. You probably should split job satisfaction and life satisfaction up onto two different scales, not have them on the same scale. And if you had two contracts on the same scale, that would mean it has multiple dimensions. And you typically don't want to do this, and you may need a factor analysis to determine the dimensionality to see if you actually have some items that are grouping together and these other items that are grouping together, and you have multiple dimensions. But factor analysis is outside the scope of this class. Another caution is that Cronbach's alpha assumes equivalency for the inter-item correlations. So meaning that differences in the inter-item correlations are just due to sampling error. So it's just by chance that our inter-item correlations are differing and we average them out to get kind of an estimate of what they all really should be. So in our example from before, all our correlations were around 0.31, but they didn't really differ a lot. But here on this slide, we can see we have a little different story. We have 0.33, 0.32, and then 0.99. That might be a red flag. If you have a correlation that is really high compared to the other ones. So it might mean that these two items are too related to each other. And what's going to happen is going to boost up your inner item, the average of your inner item correlations, but not because your scale is more reliable. It just might mean that these two items are too close to each other in some kind of way. So I'll give you a really extreme example. So say we have a self-esteem scale with only 3 items, and we have item 1, and then item 2 and 3 are really related to each other. So maybe item 2 is I am a person of worth, item 3 is I'm a person of self-worth, and so it's almost the same, right? Just the word self. And so maybe people actually will rate these two items in the same way, or most people will, and you have a correlation of 0.99. So now instead of your average inter-item correlation being 0.55, or instead of it being 0.31, now it's 0.55. So we really increased our inter-item correlation because we put these two items that were almost the same. But, I mean, that's kind of cheating, right? And if we do that, if our inter-item correlation average increases, then our Cronbach alpha jumps from 0.57 to 0.78. So now we have a more acceptable Cronbach alpha, but it's just because we have basically the same item twice. So if you have something like this and the items are a pair of items are too correlated with each other, you might consider dropping one of the items. If you have a lot of items, then it's not as big of a deal. But when you have 3, it's going to increase the inter-item correlation average a lot. But if you have a bunch of items, it's not as big of a concern. So just when you're calculating Cronbach's alpha, you should always look at the inter-item correlations and make sure there's no red flags. Also, you could have too high of a Cronbach's alpha. So if you have 0.99 as your Cronbach's alpha, it might indicate that your items are just repeating each other. So if you have a really high Cronbach's alpha, then your inter-item correlations might just be like super high. And it kind of relates to the last slide where we talk about having 2 items that were so correlated with each other. Maybe like all your items are just almost repeating each other. Maybe not as extreme as my last example, but they're just getting at a very narrow part of your construct and you're missing out on other aspects of your construct. So you're just measuring one little part of your construct and your items are just really, really narrow, and you might want to make your items more broad to get the whole part of your construct. And lastly, and probably the most important to remember, is that Cronbach's alpha is about reliability, and it tells you nothing about the validity of the test. So a test must be reliable, a valid test must be reliable, but a reliable test is not always valid. So it's kind of like the first hurdle in validating your test is calculating the reliability. So if it's reliable, then it means it could possibly be valid, but it doesn't mean it is valid. It doesn't mean it is accurate. It doesn't mean it's actually measuring what you meant to measure. It's just consistently measuring the same thing with multiple items. It doesn't mean it's measuring what you think it is. I'll leave you there.